So in this video, we are going to quickly run through a demo of k-fold cross-validation. So let's just look at the data. Looks like that. And then what we want to do, we want to divide the data set into how many of our pieces. Here it looks like I'm going to do a 6-fold cross-validation. So we want to divide it in 6 pieces, and we want to compute validation error as a function of, say, model complexity, keeping one of the 6 pieces as a validation set and the other as a training set, and then do that for every one of the validation sets, and then sort of sum over and average over all possible things. And this is a way of finding what the optimal model complexity is, or optimal polynomial model for our particular case. Okay, so how do you split this into 6 pieces? In the classic sort of k-fold cross-validation, we divide the thing into 6 equal pieces. MATLAB provides a function called cross-valend, which actually divides it into approximately equal pieces. So I just ran that little piece, and it created this array called indices, which is this 40 by 1 array. So the original data set, notice that it's a 40 by 1 array as well. And so indices is a 40 by 1 array. And if I look at indices, its numbers, integers, 2, 3, 4, 5, 4, 2. It's basically numbers from 1 to 6. Okay, we asked for 6-fold cross-validation, which means we want to split the data into 6 pieces. And what this indices array is it's assigning each element of your data set to a particular one of the 6 pieces, 6 sets, right? So it's saying data point number 1 goes to the second set. Data point number 2 goes to the third set. Data point number 3 goes to the fourth set. Data point number data point number 4 goes to the fifth set, data point number 5 goes to the fourth set, and so on and so forth, right? So each data point is assigned to one of 6 sets. And it turns out that it doesn't split the total data set equally, but approximately equally. There may be a few more or less in some of the sets, okay? So if I want to pull out all the data points that are in set number 3, let's say, we can just do that. And it's now the second data point, this data point, this data point, etc. are belonging to set number 3. Okay. Okay. So what do we do next? We now systematically go through polynomials of different order and construct the best fit for each polynomial order, find the mean square error for each polynomial order. And we do that for each one of these 6 sets being the validation set and the others being the training set. So let me do that. Let's run this thing. Let's run this piece. Before I run this, let me just point to a couple of things. So we're going to do this from k equals 1 to 6, basically, for 6-fold cross-validation. And for each of them, I'm going to say the validation set equals indices equals k. So when k equals 1, the validation set is all the indices that are equal to 1. When k equals 2, validation set is all the indices that are equal to 2, and so on. And then the training set is not of the validation set. This tilde means not, right? So if you have a list of zeros and ones, something like that, and then you go not, sorry, that tilde of a and s, which is this variable, you will get everywhere there's a 0, there's a 1, and so on, right? So what we're saying is the training set is everything that is not in the validation set. And then we go xlist in the training set is equal to xlist of this variable train. Same for ylist, and then xlist test or validation. People might use those words interchangeably in this context. We can just go, the validation set is actually the test set, doesn't matter. Let me just replace all. Okay. Okay. So, and then we loop through, for each validation set, we loop through all the polynomials. We store the mean square error for the training set. We store the mean square error for the validation set. And we do that as a function of polynomial degree. And then we also do that while changing which one is considered the validation set. So that's why there are two loops. One loop loops over the validation sets. One loop loops over the polynomial degree. And once you compute all that, we can then plot the mean squared error for the training set, which is meant to go down monotonically. And then the mean squared error for the validation set is supposed to go down and then up. So let's see if that works. I guess I didn't run this thing. Let's run that. Then let's run this. Okay, so that's what that looks like. The blue is the training error, goes down, 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 down. And then the validation error goes up a little bit and then down to some value at 3, and then seems to go up, right? So 3 is the optimal degree of the polynomial. So mean validation error is minimized at n equals 3, which is in fact the optimal value for this data set. I, in fact, used a cubic polynomial to construct this data set. So that's basically k-fold validation. You might notice that there is still some quote-unquote variability or noise in the validation error, although it's much nicer. Something we can do is actually repeat this whole process a few more times and average over all those. Actually, this whole process, starting from here to here a few times and average over all those validation error curves to actually get a nice, smoother validation error curve. Anyway, so that's basically k-fold validation, cross-validation, and I guess one of your homework problems involves essentially using this program, but for your data set. Let me stop there.